Welcome to ePadasala lecture series in computer science. In this module, we are going to deal with approximation algorithms. Probably you can recollect last few modules we were concentrating on randomization algorithms for solving NP complete problems. Approximation algorithm is also another way of approaching NP complete problems. The learning objectives of these particular modules are as follows. To understand approximation algorithms, we will discuss about the need for approximation algorithms, and then we will take some couple of problems like vertex-cover, set-cover and traveling salesperson problem, and then we will try to solve those problems using the approximation approach. Fine. What is an approximation algorithm? Probably you can recollect in earlier modules we discussed about the NP complete problems. The problems like traveling salesperson, Hamiltonian are all good examples of NP complete problems. What are NP complete problems? NP complete problems do not have the polynomial time solutions. In other words, these algorithms are exponential in nature, and as the input size increases, the amount of resources becomes larger and larger. In that context, the solution of NP complete problem becomes very difficult. We had already discussed that these problems do not have any polynomial time solutions. So, what is the solution for this? If we encounter these problems in the real time world, in real world many problems are NP complete in nature. For example, weather forecasting is one example of NP complete problem. In modern day, we have to find solution for these problems. Last module we discussed the method of using randomization as a possible way of approaching these problems. So, what we did actually was that we introduced the randomization as part of the problem. We designed algorithms using the randomization approach, and we had seen that the introduction of randomization solves the problem. I gave you a simple example that if the production of a transistor goes beyond certain limit, then the quality check can be done by random sampling. We can arbitrarily pick up some of the kits and we can test for quality, and based on that we can find some sort of a solutions. In the same manner, approximation algorithm also can be used to solve these problems. Approximation algorithms use some sort of a heuristics to solve the problem in a polynomial time. So, the key is very simple, that is the algorithm should run in polynomial time, and these algorithms will not give the exact solution, but instead will give the near optimal solutions. What is the near optimal solution? Fine, we had seen earlier that the optimal solution is one solution which maximizes or minimizes the objective function while satisfying all the constraints. There are many candidate solutions for a given problem. Out of all the solutions, only certain solutions are capable of maximizing or minimizing the objective function while satisfying some of the constraints. These solutions are called optimal solutions. Approximation algorithm will not guarantee the optimal solutions, but it will provide a near optimal solution which in most of the circumstances are more than sufficient. That is the reason why we are going for the approximation algorithms. So, we can view algorithms as two categories. One is exact algorithms and another is approximation algorithms. Exact algorithms will solutions which are exact in nature. In normal circumstances, we will go for the exact solutions and we will use exact algorithms. But in a extraordinary situation where we have a problem that is NP complete, we will go for the approximation algorithms which produces the near optimal solutions. Here the basic premise is very simple, that is the optimal solution which we are getting through the approximation algorithm will not deviate much from the optimal solutions as close as possible. In other words, the difference between the actual solution and the approximation solution is going to be a little factor. So, using this particular logic, we are going to design algorithms and we are going to apply problems which are otherwise very difficult to solve. Fine. How to design approximation algorithms? So, the way to design approximation algorithm is to use the principle of restrictions. What is meant by restrictions? We can restrict some of the constraints and we can solve the problem. Fine. We will take one simple problem, traveling salesperson problem or traveling salesman problem. Both are same. So, what is the problem? We have to start from the city, then we have to visit all other cities only once, and then we have to come back to the original city. This is the problem. We had seen that this problem is a very difficult problem to solve. Therefore, we are planning to approach this through approximation algorithms. So, we can remove certain restrictions or constraints. For example, we can relax the constraint that the city should be visited only once. So, what we will do is we will try to remove that restrictions and then we will try to solve. But unfortunately, that is not the solution for that particular problem. So, what we will do is we will try to reintroduce that constraint back into the problem and then we will try to refine the solutions. So, in that particular manner we will be able to get a solution. So, the logic is very simple. Try to see the problem, try to solve it. If the solution is not possible, then possibly it is a NP complete problem. So, try to give you a proof that it is a NP complete problem. Then once a proof is given, then we will try to solve that in an alternative manner. We can go for the randomization approach, and if that also do not work, then probably we can approach the problem using approximate solution. So, what we can do is we can restrict some of the constraints or we can relax some of the constraints, then we will try to solve the problem, then later on we will try to reintroduce those constraints so that the solution is right. So, this is a logic of all these algorithms. So, we are going to use some sort of a strategy for that. So, we will use heuristics for this. So, what is a heuristic? Heuristic is nothing but the rule of thumb which normally gives solution and occasionally it may fail also. So, we will try to introduce some heuristics and then we will try to solve. We will also use greedy approach or dynamic programming or the integer programming for solving these sort of problems. We will review one by one. Fine. Let us assume that we have a problem, and let us assume that the actual cost of the optimal solution is C asterisk. So, in other words, suppose if the problem is given and if the actual solution, optimal solution is found to be C asterisk, and the cost of the solution that is generated by the algorithm A is C, then we can say that the approximation ratio is nothing but C by C star or C star divided by C. So, we have to take the maximum of this, and this is what we are calling respectively for maximization and minimization problem, and this ratio is what we are calling as the approximation ratio. If the approximation algorithm has got rho of n, that is the ratio of the original and approximation, or the approximation and original, when we take the maximum of that, we are getting the approximation ratio rho of n. Suppose if the algorithm has got an approximation ratio of rho of n, then we can call that particular algorithm as rho of n approximation algorithm. In other words, we can say that the algorithm exhibits the characteristic of rho of n. So, in short, we can summarize like this: the approximation algorithm should run in polynomial time. This is very crucial. This is the most important point. If the algorithm is not running in polynomial time, then it is of no use. It is not an approximation algorithm. Second point is we should get an approximation ratio which is what is say acceptable. Fine. We will take one simple example for this. Suppose if the total weight of the minimum spanning tree is going to be 10. If this is the case, then let us say I am designing one approximation algorithm and I am trying to generate the weights, and if the weights are always smaller than 15, then we can say the approximation ratio is 15 by 10, that is going to be 1.5. In this case, this algorithm is called 1.5 approximation algorithm. What is the range of this? The range is if rho of n is going to be 1, then we can say that the algorithm always finds the optimal solution, and if it goes away from 1, then we can say that that is the approximation under which the algorithm works. In other words, what we are trying to say is that this algorithm can find the solution within the range of rho of n. Using this principle, we can discuss the approximation algorithms, and we will take some examples of that. Then we will try to solve these problems using the approximation approach. First, we will take the problem of vertex cover. Vertex cover is a NP complete problem which is very difficult to solve in the normal circumstances. In earlier module, we have given a proof of why vertex cover is going to be a NP complete problem. Let us try to discuss the approximation solution for this. What is an vertex cover problem? Assume that we are given a undirected graph G is equal to V comma E, where V is nothing but the set of vertices or nodes and E is a set of edges. If this is the case, then we can say the vertex cover V prime such that V prime is an element of V. So, that means all the vertices should be there, and if we take any edge u comma v in E, then we have to show that either u or v is the element of what you say v prime. So, that means in other words we have to show that for every edge at least one vertex of that edge belongs to the set of v prime. So, if we are able to construct such a v prime, then that is what we are calling as the vertex cover. What is the size of vertex cover? The vertex cover size is nothing but the number of vertices that are as part of v prime. This is what we are calling as the size of the vertex cover. Fine. Let us give some small example of what exactly we mean by the theoretical definition which we said so far. Assume that this is the undirected graph. You can see that there are 6 vertices or nodes. So, you can say that the aim is to find vertex cover. So, hypothetically let me assume that the vertex 1 and 2 are considered as the vertex cover. So, if the red vertices 1 and 2 are considered as the vertex cover, is it sufficient or not? Fine, it is not sufficient, because you have the instances like 4, 5, 5, 6 and 3, 6 are not covered by the v prime. In other words, if I take the edge 4, 5, then you can see neither the vertex 4 nor the vertex 5 is part of vertex cover. So, that means just a selection of node 1 and 2 is not sufficient for vertex cover. So, that is the logic. Fine. So, now you take this particular case. Fine. Can we call the vertex cover as a set of vertices 1, 2 and 6? Fine. Again you can see that it is not vertex cover because the edge 4, 5 is not covered by that. So, that means it is not an vertex cover. Fine. Take this particular example. If I take all the vertices as the vertex cover, can we call this as a vertex cover? Means yes, all the edges are covered, but the problem is it is not an optimal solution. In other words, you can't say this as the best solutions. So, in other words, we can say that the vertex cover problem is a problem where we have to find the vertex cover of minimum size. In other words, in the previous case, if we want to cover 4, 5, then either 4 or 5 should be covered as part of vertex cover, then only the solution is getting completed. In short, we can say that the vertex problem is nothing but a problem where we have to find the vertex cover with the minimum size. Fine. How to find the approximation algorithm for this? The approximation algorithm is something like this. So, initially what you say, I am considering the cover as null. So, I am considering E prime as the set of all the edges of the graph, and I am entering into the loop. So, when the edge list is not equal to null, so what I am trying to do is I am going to randomly pick an edge u comma v, and I am going to put u comma v into the set cover. So, once I put that particular edge, then I will try to remove all the edges that are covered by u comma v from E prime. So, this process I will continue till all the edges are considered. Finally, I am going to return this cover C. This algorithm we can call as two approximation algorithm, where the approximation ratio is going to be 2. Fine. What is the proof of that? Let us assume that the minimum vertex cover is u asterisk. So, let us assume that the approximation algorithm that we designed so far is returning a value of u. Then the edges that are present in the approximation algorithm list is going to be A. Then we can say that the vertex in u star can cover only one edge in A. So, that means you can say that the size of u star is going to be A. But in the algorithm that we designed so far, what we are doing is we are taking the edge u comma v, and then we are trying to add both u as well as v into the cover. So, that means for every edge there are two vertices in u. If that is the case, you can say that the size of u will be the twice of A. So, you can combine this with your earlier observation, and you can say now that the size of u star is going to be greater than or equal to the size of u by 2, and by realigning the terms we can say that the ratio of u and u star is going to be lesser than or equal to 2. So, what we have seen earlier is the ratio of the original and the approximation, or the ratio of approximation by original. If we take maximum, then that is called what you say the approximation ratio. So, this is a minimization problem. Therefore, we are taking the ratio of approximation by original, and it is going to be lesser than or equal to 2. Therefore, we can conclude that this is a two approximation algorithms. This is how we can solve the problem of vertex cover. Another problem that comes very handy is a traveling salesman problem. So, TSP, we have seen this problem many times. So, the logic is very simple. You have to start from a city, you have to visit all the cities, and then you have to come back. So, that means we have to find the minimum route as part of this problem. Already we had seen that this is a NP complete problem. So, that means there is no polynomial time algorithm available for that. So, for this reason we can go for some sort of an algorithm with the constant approximation ratio. So, what is the restriction we are going to put? We are going to relax the constraint that a city should be visited only once. We will relax, we will solve, then we will reinforce all the constraints. So, what is the algorithm for this? So, we are going to find the minimum spanning tree for x, x of the given graph G. You know very well MST is nothing but all the vertices will be maintained, but not all the edges will be present. We will choose one node as the root R, then we will visit all the vertices only once. Suppose if there is no connection, then we will introduce that path. So, this will create a duplication. We will perform the pre-order walk. So, we will get the path with duplication, but what is the original problem? The original problem says there should not be any duplication. So, what we have to do is we will try to eliminate the duplicate vertex in the obtained path, so that we can find the solutions. So, we will take one numerical example for this. Let us assume that these are the nodes of the graph. So, what I am going to do is I am going to find the minimum spanning tree for this. So, this is the minimum spanning tree. So, I am going to choose A as a root. So, as per the algorithm, what should I do? I should find the what is a pre-order tree walk. So, I am just performing the walk. So, it is A B, then C, then there is no path. So, that means I will backtrack to B and then I will visit H. You can see that now I am in a dead end. So, that means I will just backtrack to B and then A, and then I will visit D, and then I will visit E, and then I will visit what you say G. This is the path I am getting out of this. But this is not a traveling salesperson problem solution, because in traveling salesman problem we have to start from A and then we have to end in A. So, that means there is no route from H to D. Okay. So, what I will try to do is I will try to introduce a path artificially, so that I can have what you say a path like this. So, that means I will visit A, B, C, H, D, E, G, and then from G I will go back to A. So, that means you can see that this is the solution for the given problem. Fine, the last example is going to be a set cover problem. The logic is very simple. I will have a set X, and then I will have the family of subsets of X. So, I have to find F such that it covers X. This is what the requirement of the problem. Like a vertex cover, I have to find the set cover with minimum size. This is the approximation algorithm for that. So, initially I will set u equal to X, initially cover is equal to null. When u is not equal to null, then I will select S such that it maximizes the S interjunction of u. Then I will remove this set from the universal set, and then I will add this as the cover, and then I will go for. So, this is example for this. So, you can see that a set subset is A B, that is F1, B itself is a separate subset, it is F2. Similarly, C is another subset, it is F3, then D is going to be F4, and A itself is going to be F5. So, the logic is very simple. I have to what you say select the subset to cover all the sets. So, that is a thing. So, if I select F1, what will happen? F1 will cover A and B. So, what is left? C and D is left. So, to cover C, I have to select F3. Then what is left? D is left. So, I have to select what you say F4. Therefore, the solution is what you say F1, F3 and F4. This is the what you say solution for this particular problem. So, you can view this problem as something like a patient and doctor, where you have to choose the minimum number of doctor to cover the maximum patients. So, if you correlate this problem with the given scenario, you will understand that this problem is exactly doing the problem of covering the patient by the minimum doctors. Okay, this is a solution. What is the summary? Summary is very simple. Approximation algorithms are very effective, they are very fast, solves a problem in polynomial time. Vertex cover problem can be done using approximation algorithm. TSP problem can be solved by approximation algorithm, and similarly the set cover problem also can be solved by approximation algorithm effectively. These are the references. Thank you.